Okay, welcome to our video about balancing chemical equations. Sometimes if you see a flask and it's bubbling over, they might just be overreacting. Okay, that's all right. Not everyone's a winner. Just gonna keep motoring on. All right. So, to talk about this. Sorry to keep moving myself around here, but I don't want to get in the way of what I want you to see. So I'm just going to flash back to something we talked about not too long ago in a previous video, which was the law of conservation of mass. So the law of conservation of mass simply says that as long as you have a system that's closed, right, it doesn't really have any way for matter to get in or out, stuff doesn't appear or disappear. That matter is always conserved. Stuff doesn't just disappear or appear. Right, so the analogy I used was a closed pot on the stove. It's heated, so the energy is getting transferred, but the matter itself is not, right? So the steam is, you're getting steam, but the steam's staying inside of the pot. So that's the idea of the law of conservation of mass. And it's important that what we do here is we just apply that law to chemical equations. So what we need to focus on here is it should be a fairly straightforward concept. Because we have this law that mass doesn't just appear or disappear, that means that the amount of reactants, that means the mass or the number of molecules of reactants in a chemical reaction must be the same as the amount of the products. So what goes in and what comes out are always the same. And if you're really properly writing the equation for a chemical reaction, you should have accounted for all of the possible substances, even the things that we sometimes forget about, the gases or something that go somewhere. Let me show you an example of what I'm talking about. Let's say that we have 100 grams of substance A, and there's a decomposition reaction, right? That's, if you remember from our types of reactions, that means that's one substance is broken down into two or more substances. So substance A is split into substances B and C. It was a decomposition reaction. If 75 grams of substance B is produced, what's the mass of substance C that's produced? And so this is just a very simple algebra problem, if you will. So the reaction we could say is A yields B plus C. There's our decomposition. And so we had 100 grams of A, and we know that it produced 75 grams of, I'm sorry, that should be for B, plus X, right? X would be the mass of substance C that's produced. X would be the mass of substance C that's produced. And so if we simply solve that by subtracting 75 from both sides, we'll find out that that amount of C, sorry, that should say C, not B, is 25 grams, right? There should be 100 grams, if there were 100 grams of reactants, there should be 100 grams of product as well. Okay, and so what the law of conservation of mass does for us in chemical equations is it tells us we have to balance them, right? They have to be balanced. That means you have to figure out how to make sure that reactants and products are the same. So we do that using coefficients. We use coefficients to balance equations. And so you might remember, because we've seen them before, the coefficients are these numbers, whole numbers, right? No decimals, no fractions, whole numbers that we put to the left of a chemical formula. So this is a chemical formula I've shown you before, C8H10, N4O2, that's caffeine, right? Put the 3 to the left of it. And that tells us, well, in this particular instance, we have 3 molecules of all of this. And so the total number of atoms of each type is 3 times that, 3 times that, 3 times that, right? So those are coefficients, whole numbers placed to the left of a chemical formula that multiplies the number of atoms of each element in that formula. As always, if you're falling a little bit behind on taking notes, no worries, just pause the video and then catch back up. Okay. So let me show you what I mean by balancing with a nice example here. So I'm going to take the idea of burning methane, right? And so methane is CH4, right? And when we burn it, we're going to add some oxygen to it. That's the reaction, is methane plus oxygen, and then it yields carbon dioxide and water, right? This is natural gas, so just like the stuff coming out of your stove, if you have that kind of stove at home. So what's also not listed here is that a ton of energy comes out, a lot of light and heat. Now let's examine how many of each element are on both sides. So we've got the reactant side on the left and the product side on the right. So on the reactant side, how many carbons do we have? Well, I don't see any subscripts or coefficients, so I only have one carbon. I'm going to write that down right there. How many hydrogens? Well, I see a 4 subscript. And there's none over here, so I'm going to write 4 hydrogens. And how many oxygens? Well, I see that subscript 2 there, so I'm going to say, okay, I got 2 oxygens, right? Now let's look at the same thing on the other side. How many carbons? I only see 1, so I write down 1. How many hydrogens? I see 2 here, so I'm going to write down 2. How many oxygens? There's 2 here, and there's 1 here, so we have to add them. 2 plus 1, that's 3, right? So this is an unbalanced chemical equation. See the unbalanced? Because there is more hydrogen on the left side and more oxygen on the right side. And that's not possible, right? It all has to go somewhere. It doesn't just disappear or appear, right? These extra hydrogens don't just disappear. They have to end up on the right side somehow. And these oxygens don't just appear, they have to get there from somewhere. So we fix this by balancing using coefficients. So let me show you how we can do that. So what I'm going to do here is just add a 2, a coefficient of 2, right next to this H2O. Because I had 4 hydrogen over here, but only 2 over here. So if I add in that 2, that becomes 2 times 2 hydrogen, or 4. And then I have 2 times 1 oxygen, plus 2 oxygen over here. So I end up with 4 oxygen, right? So now my number of hydrogens is balanced. I've got 1 carbon on both sides, I've got 4 hydrogens on both sides. But I still have a bit of an unbalanced situation here. I've got 2 oxygens and on the left, 4 oxygens on the right. So I got to do something more. Let's see what else can we do. Well, we can throw a 2 in front of this O2 over here. Now, because I've multiplied that O2 times 2, I have 4 oxygens on the left. So I've got 1 carbon, 1 carbon, 4 hydrogen, 4 hydrogen, 4 oxygen, 4 oxygen. And that is a balanced chemical equation. So that's really what we're all about here, is trying to make these coefficients, trying to stick these coefficients in so that we don't end up with any atoms of some element that appear or disappear without having come from the other side. Okay, so a couple tips when you're trying to balance a chemical equation. When you're trying to balance a chemical equation, the first thing you want to do is do what I just did in those examples, which is write out the number of atoms of each element on both sides of the arrow. So again, this way, notice that that's what I did, right? I wrote down how many carbons, how many hydrogens, how many oxygens on the left. How many carbons, how many hydrogens, how many oxygens on the right. And I keep them in the same place, right? The carbons are on the first line, hydrogens are on the second line, so I can see it more easily. Then the second thing is just remember you can only change coefficients. You can only put numbers to the left of each compound or molecule. You cannot change subscripts. That doesn't happen because that's not the point. The point is the substances that go, we have substances that go in and substances that come out, and the subscripts tell us what those substances are. And then we're going to just try different coefficients until all of the numbers are balanced. Right? So we're going to move those numbers on the left. We're going to try different combinations and see how we get to where we want to be. All right? Pause the video if you need to finish taking notes. So let's look at an example. This is a long-sounding equation with 5 different elements. So it seems like it might be a lot, but actually this one is fairly straightforward. So we have, on the left, we have 1 hydrogen, 1 chlorine, this is a Cl, 1 calcium coming from here, 1 carbon coming from here, and then 3 oxygens coming from here. Okay, so what do we have on the other side? How many hydrogens? We have 2 from that molecule. How many chlorines? We have 2 from that molecule. How many calciums? 1 right there. How many carbons? 1 right there. And how many oxygens? Well, we have 2 here, plus we have 1 there. So don't forget to take the extra moment to make sure that you looked at all of the different substances, all the compounds or molecules involved, and counted all of the atoms of a certain element. So now we can see that we have the same number of calciums, carbons, and oxygens, but we have a different number of hydrogens and a different number of chlorines. How can we fix that? Well, we're going to have to add a coefficient. And it so happens that because we have 2 hydrogen and 2 chlorine over here, but only 1 and 1, the hydrogen and chlorine are next to each other on the left side. So that means easily, if we just put a 2 right there, we're going to get 2 hydrogens and 2 chlorines. And indeed, If you put a 2 there, you can see I've changed the counts. I've updated the counts, and now we have the same numbers of both on both sides. All you had to do is add in that 2 next to the HCl. And if you're curious, this is what we call the Tums reaction. So HCl, that's hydrochloric acid, that's stomach acid, right? And that's the stuff that causes heartburn when your stomach acid leaks up into your esophagus. And Tums is calcium carbonate, which is CaCO3. So when you add in the CaCO3, it bonds to the HCl and gets rid of some of that acid. That's why people take Tums when they get heartburn. Okay, here's one for you to try. You've got Cl2, that's chlorine gas plus KBr, potassium bromide, and that's in a single replacement reaction turning into potassium chloride and Br2, that's bromine. So I've written down the numbers for you here. Try this one on your own in your notebook. Pause the video and then come back. Okay, let's see how you did. So on the left, we've got 2 chlorines, 1 potassium from there and 1 bromine. On the right, we've got 1 chlorine from right there, 1 potassium from right there, and 2 bromines. So you can see the chlorines and the bromines are the things that are not matching. So what can we do? So when you've got that situation, you think, well, let me double some things and see what happens. So if I put the 2 in front of this KCl, I end up with 2 chlorines on the right side, which matches my 2 chlorines on the left. It also gives me 2 potassiums. So because I did that, I better put a 2 over here so that I get 2 potassiums over here. And conveniently, because I did that, the bromine gets doubled over here, and the bromine's already doubled over there. So this, just adding those 2 coefficients, gets the job done here. Cool. Let's look at a slightly more difficult example, because sometimes you really do have to do this by trial and error. So this is copper 1 sulfide and oxygen. And in a replacement reaction, the oxygen and sulfur swap places, so you end up with copper 1 oxide and sulfur dioxide as your outputs. So let's see what we have. On the left side, we've got 2 coppers. We've got 1 sulfur, and we've got 2 oxygens. Okay. On the right side, we've got 2 coppers. We've got 1 sulfur, just 1 right there, and then we've got 1, 2, plus 1, 3 oxygens. So you can already potentially start to see that because the difference is just 3 to 2, this might take a little more thinking than the last one. Pause the video, try this one on your own. Remember, it may take you a few tries to get this one right. And then come back and we'll see how we did. Okay, welcome back. Let's see how we did. So we have to first try to figure out what we can do to deal with this oxygen and oxygen problem. There's 3 on the right, there's 2 on the left. So let's see what we can do. Well, we can put a 2 next to the Cu2O so that we get more oxygen on the right. So that gives us 2 plus 2, which is 4 oxygens, and then 2 times, we even that out on the left side by adding a 2 here. We have 2 times 2 or 4 oxygens. Cool, the oxygens are balanced, the sulfurs are also balanced, but what happened here? Well, when we put this 2 here, we actually end up with 4 coppers on the right, and we still only have 2 coppers on the left. So that still leaves us with more to do. Let's keep going. So the other thing that we can do is say, well, now that we have 4 coppers here, let's put a 2 on the left side so we get our 4 coppers. Now we have our 4 coppers, and we have our 4 oxygens. Cool, except that now we ended up with 2 sulfurs here, and we only have 1 on the right. So we still have a problem, right? So putting 2, 2, 2 here did not work. So that is kind of basically a dead end, because you can't add in another 2 on that SO2. You're going to keep messing up the oxygen situation. So let's try something different. So what I did here was I involved a 3, right? So you had those funny ratios because it was 3 to 2. It wasn't just even numbers or odd numbers on both sides, you even and odd, and that tells you probably need to use some even and odds here. So what I ended up doing was, again, trying to balance out the oxygens. We got 2 times 2 is 4, and 2 times 2 is another 2, or sorry, 2 times 1 is another 2. That gives us 6. Well, that's easy to balance over here because 3 times 2 is 6, right? And then to make sure that everything else is balanced, we look here. So we made 4 coppers. That means we need to put 2 there. 2 times 2 gives us 4 coppers here. And conveniently, because we had 2 sulfurs here, we also did that over here. We end up with we end up with a total of 2 sulfurs on both sides. So I had to try something different, try some different numbers.